What did we talk about yesterday? Well, I finished up that example, right? You guys, that all made sense yesterday. It was two little. It was one video compressed. I put it on my YouTube channel. I split it up into separate parts, so it's easier to find what you want to find. So finished up the problem from the previous day, and we started to look at horizontal asymptotes, right? Essentially, just talked about what it means to be a horizontal asymptote. Well, it means very much the same thing that it means to be a vertical asymptote. So, couple differences. A vertical asymptote is like dividing the two-dimensional ant universe into separate universes that are inaccessible. It's like it's carving separate spaces out. You cannot cross a vertical asymptote. That's where the function is undefined, so you can't go there. Now you can cross a horizontal asymptote. That is no big deal. A horizontal asymptote is really just saying as x approaches positive infinity or negative infinity, is there a horizontal line that the function is more and more closely adhering to, right? And again, it's that same principle. Like if I'm walking towards the door, if I cut my distance to the door in half every second, I am approaching the door even though I don't get there, right? And we looked at an example yesterday on the video where we took this function, f of x is sine x over x. That's what the function looks like. If you look at relatively small numbers, it doesn't look asymptotic at all, right? But if you zoom out, you start to see that, yeah, as we go out to the tails of the function, as x tends towards positive or negative infinity, these oscillations get damped out and it starts to more and more closely hug the x-axis, right? So way out there and way out there, the x-axis is a good description of the behavior of the function, right? Okay, give me thumbs on that concept. Does that all make sense? Okay. All right, so I gave you also yesterday, there's a theorem here. If you have a function divided by a power of x, as x goes to positive or negative infinity, the bottom of the fraction is going to explode and the top of the fraction is going to stay fixed. And what happens to a fraction if the bottom gets huge? The value of the fraction goes to zero, doesn't it, right? Okay, and that explains that, well, the whole horizontal asymptote thing. Okay, so let's explore some specific examples and see if we can see some patterns to save ourselves work later. We're going to take a limit of this rational function as x approaches plus or minus infinity. Okay, what's some algebra that we could do here? Well, I'm going to kind of zip through this. I'm going to show you a way, and stop me as I'm going through this if there's anything you need me to go slower on. The biggest power of x that shows up in either polynomial is x squared. So what if I were to factor out an x squared? Okay, if I factor out an x squared from the top and the bottom, on the top, let's do the bottom first. If I factor out an x squared on the bottom, what's left behind? So I'm undistributing an x squared. What's left from that term? 3, okay? I can prove it because if I distribute the x squared, I would get 3x squared. Okay, this one's a little weirder. What's going to be left there? If I'm factoring out an x squared, I'm dividing it away from each term. So in other words, x squared times what is 1? 1 over x squared. There you go. Good. Okay, give me thumbs on that. Is that making sense? You might be thinking that's a very weird thing to do, right? Why would we factor something out and leave ourselves with a fraction? Well, normally we wouldn't, but in this case, you'll see why. On the top, if I factor out an x squared, what's going to be left behind? Well, x squared times what would give me my 2x? You can kind of see here that to get the 3 plus 1 over x, all I really did was just divide each of those by x squared. When I factor out something, I'm dividing it away. So 3x squared over x squared gave me my 3. 1 over x squared Gave me my 1 over x squared. So it'd be 2 over x, wouldn't it? Because 2x over x squared is 2 over x. And then here I'd get 5 over x squared. Okay, now I'm going to pause there. Now, do not, like, if you're unsure about something, let me know. Because if you are, somebody else is, guaranteed. How are we doing on this? Does that make sense? Okay. All right, so this is as x approaches plus or minus infinity. Well, in my limit, algebraically, look, I could cancel the x squareds, right? Cancel those factors, and I'm taking a limit of a different function that's going to be the same, except possibly at the value of 0. Well, yeah, except possibly at the value of 0. Okay. Now, this new function that I get, let's change colors. What happens if I take my limit, meaning I evaluate my limit, evaluate directly? If I let x go to the infinities, what happens to each of these fractions here? If x is going to positive or negative infinity, what value does the fraction approach? 0, right? Because I've got a constant divided by an infinitely large number, which is very, very small, right? So those are all approaching 0. So we end up with, when we take our limit then, we end up with the result 0 plus 0 over 3 plus 0, right? Everybody agree? Okay, well, if the limit of this function as x approaches plus or minus infinity is 0, does it have a horizontal asymptote? Now think about what that's saying, what that's asking. The limit of the function is saying what y value is the ant expecting to step on as he approaches plus or minus an x value of plus or minus infinity. The ant is expecting to step on an x value of 0 as x value or y value of 0 as the x values get bigger and bigger and bigger. So what does that look like? That's a horizontal asymptote, right? Like if we graph this thing, what's this going to look like? Okay, let's just graph this function. 2 2x plus 5 over 3x squared plus 1. There it is. There's my function. We can zoom in. There it is. Okay, if we zoom way out, yeah, that's got a horizontal asymptote, doesn't it? Everybody see that? Like, in fact, let's do this. I'm going to zoom way the heck out, but I'm going to keep the y. I'm not going to zoom out on the y-axis, only on the x-axis. So if we make y go from, how about -4 to +6 by 1s, and we'll let x go from -100,000 to +100,000. Well, look at that. Doesn't that look an awful lot like the line y equals 0 when I get out on the tails? Okay. So that's reinforcing that fact then that a horizontal asymptote is nothing more than the value of the limit at infinity if we get a constant. Like in this case, 0. Because that's 0, our horizontal asymptote, I'll just do that, is the line y equals 0.
asymptotes are constant, are where you get a constant when you evaluate a limit at infinity.
Right, when you take a limit at infinity and you get a constant value, that corresponds to a horizontal asymptote. Exactly, yeah. Okay, so that looked like a lot of algebra though, didn't it? I mean, it works, it's fine. We could do that same process every time, but there's an easier way to do this. Remember the video I showed you guys yesterday, right? What was the moral of the story of that video? If we took a big polynomial and we zoomed way out, which was the term that dominated the behavior of the polynomial? The leading term, right? Everything else was insignificant. So this doesn't work except for the fact that we are approaching the infinities, right? Because we're approaching the infinities, we're assuming that these are extremely large x values that we're plugging in. So only the leading terms of the polynomials in the top and the bottom are going to really contribute, right? The other stuff just goes away. So this limit of this rational function, as long as we are approaching the infinities, and it could be either one of them too, it doesn't have to be both. It could be positive infinity or negative infinity, or in this case, both of them, is equal to the limit of just the ratio of the leading terms, right? It's equal to the limit of 2x over 3x squared as x approaches plus or minus infinity. Well, that's a pretty easy function to simplify. X over x squared, I could just cancel an x, couldn't I? Right? And so I just get the limit of 2 over 3x, which is the same thing as, if I want to say it, as 2/3 x, same thing. Oops. No, I did that wrong. Can't do that. Never mind. I'm thinking of something different. Thinking of a later example. Okay, if I evaluate this limit, ignore that part. If I evaluate this limit, what do I get? As x approaches the infinities, what's happening to that fraction? It's going to 0, isn't it? Right? Because I've got an x on the bottom that's exploding, but the top is stuck at 2. Isn't that easier? Right? So there's an approach. Again, I've never seen that in a high school textbook, at least. I don't know if I've ever seen that in college, but that's a great way to deal with infinite limits. All you have to do is look at the limits of the leading terms. You don't have to do all that complicated math then, right? Because these limits, these functions are different, but their limits are the same because I'm looking only out at values of x approaching infinity, right? So the +5 and the +1 are utterly insignificant on those for those big values of x. Okay? All right, so how about this one then? Let's use our new approach. We don't have to be factoring things out and canceling. Let's just use our new approach. Because I'm approaching plus or minus infinity, as we approach plus or minus infinity, the black function is the same as the limit of what function? 2x squared over 3x squared, which is equal to, I can cancel, look at this, I can cancel the x squareds. That's equal to the limit of 2/3 as x approaches plus or minus infinity. Well, what's the limit of 2/3 as x approaches anything? 2/3, yeah. There's no x's to even plug in, right? The answer is just 2/3. So what's my horizontal asymptote for this one? Y equals 2/3. Okay. All right. So then let's look at one more. How about this guy? Okay, that did do something good. Okay. How about this one? What would I do this time? Same approach. Because I'm approaching the infinities. That's equal to the limit of what? Two x cubed over 3x squared. If I reduce that, if I simplify that by canceling factors, I get the limit of 2x over 3, right? Which is the same thing as the limit of 2/3 x, if I want to write it that way. Okay, does that have a horizontal asymptote? That doesn't, does it? As x approaches infinity, this would be 2/3 times a huge positive number, so it would approach infinity. As x approaches negative infinity, I would get 2/3 times a huge negative number, so it would approach negative infinity. So that one does not have a horizontal asymptote. Agreed? And if we look at a picture of it, it looks like this, right? There's the original function, okay? And if I look at the behavior of just the 2/3 x, what do you notice? Well, for small values of x, the green function, which is, in this case, it's the red one. I got them kind of backwards, right? So that's the green function on my graph, and that's the red function on my graph. Here, let's change the colors around so they match. There we go. Now they match up. Okay, so look, the red function and the black function don't look very similar for small values of x, but if I zoom way the heck out, yeah, look at that. On the tails, the black function and the red function look identical, don't they? Okay. And we can see no horizontal asymptote there. So what can we distill away from this then? Well, we looked at 3 cases which seemed like they were specific, but they were actually pretty general. This is a case where we have a rational function where the top polynomial is higher degree than the bottom polynomial, right? The previous example, we had a rational function where the top and bottom polynomials were the same degree. And the first example, we had a higher degree polynomial on the bottom than on the top. And look what we got. Y equals 0 as a horizontal asymptote, y equals 2/3, which incidentally is just the ratio of the leading coefficients, isn't it? Right? And then no horizontal asymptote for that guy. So we could combine all that stuff into just a little set of rules that we can follow without doing any work. The guidelines for finding the limits of rational functions at plus or minus infinity is just that if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. So that gives us the horizontal asymptote, y equals 0. If the degree of the numerator and denominator are equal, then the limit of the rational function is the ratio of the leading coefficients. Okay? And finally, if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. The limit at infinity doesn't exist. Okay? So here's, for your notes, that might be helpful. We can break it down into kind of 2 parts. In the first 2 cases, horizontal asymptotes do exist, right? In the third case, they do not. Okay? Give me thumbs on that. Does that all make sense? What we're doing there? Okay? Okay, and then just for your notes, I just wanted to show you that alternately we can find the asymptotes by simply analyzing the behavior of the leading terms of the quotient, ignoring and not even finding the other terms, right? Just only look at the leading terms when we're approaching infinities and we have rational functions, okay? This is what we talked about, but again, just so this will be in the notes. Okay, so let's just do some practice here. Let's do a lot of stuff. Eventually, we're going to do tons of stuff with functions. When we get to, I guess it would be the end of unit 3. Yeah, we do what's called functional analysis, where we're going to sketch curves, where we're just going to find tons of stuff about any function I throw at you. Okay, using a combination of our knowledge of derivatives at that point, asymptotes, all kinds of stuff, symmetry, and that's really cool stuff. But for now, we're just kind of getting started. let's only look for asymptotes. Okay, let's find horizontal and vertical asymptotes. Let's start off with vertical asymptotes. How about? Okay. Are there any vertical asymptotes? What do you think? Or if you aren't comfortable, you're not sure yet, tell me how would we know? Tell me some stuff about that. How could we find out? What are the criteria? And really, it's just a single criterion for a vertical asymptote. What has to be true for there to be a vertical asymptote when I evaluate the limit? What kind of outcome do we get that says, vertical asymptote, if I evaluate this directly? Remember that? Zero on the bottom and something non-zero on the top. Okay, good, perfect. So a vertical asymptote always corresponds to a unique zero of the denominator. Do you understand why I use the word unique there? It's a zero only of the bottom. It's unique to the bottom. It's not a zero of the top. Okay, what's the only zero of the bottom? 2. Is 2 a zero of the top? No, if I plug 2 into the top, I don't get 0, do I? Who cares what I get, but it's not 0. Agreed? Okay, so then we would say that because is a unique zero of the denominator, x equals 2 is a vertical asymptote, right? We know something about this thing. We have a vertical asymptote at x equals 2. Okay, do we have any horizontal asymptotes? No, we know that for sure. How do we know just by inspection? Okay, good, because it's a rational function. And again, let's remind ourselves, rational function just means polynomial divided by polynomial, right? The top polynomial or the polynomial in the numerator is a higher degree, meaning has a higher exponent than the degree of the bottom denominator. And so we know right away from our list of rules, those rules right there, right? Rule 3, there's no horizontal, or there's no limit at infinity there. So there's no horizontal asymptote. We don't get a constant value when we take a limit at infinity. Okay? So this one, we've only got one, and it's a vertical asymptote. And let's just show that. Let's just demonstrate. Here's what this guy looks like. Okay, there's my function. And sure enough, there's the vertical asymptote, right? If we see that dashed line there, if we zoom out, we can see that this function sticks to that line. There's a top part up there too that we didn't see initially, right? Everybody see that? Okay, let's compress the x-axis a little bit so we can see this better. Let's just go -10 to +10 on the x's. That better? Look, the y's are all stretched, but the x's are not. Is it hard to see that asymptote here? Let's make that better. There. Okay. Give me thumbs. Does that all make sense? Okay. And notice there are no vertical asymptotes. Okay. Okay. So what about something like that? Yikes. What's going on there? Is that a polynomial on top? It's not, is it? No, not a polynomial. What are the characteristics of a polynomial? It has to have real number coefficients and whole number exponents, right? Well, that term does not meet the criteria, right? That's not a real number coefficient times the power of x. It's a sign of a power of x, totally different. But can we think about this in a similar way? If we're taking limits as x approaches plus or minus infinity, what can you guys tell me about the behavior of that term? What's that going to do? Obviously, the 6x term is going to get infinitely big at the tails because it's got an x in it, right? It's got a power of x. How big is the sine x squared ever going to get? 1? Between 1 and -1. It's bounded, isn't it? Right? That term is bounded. And so even though it's not constant, it's bounded between -1 and 1. And so in the limit, as x approaches plus or minus infinity, is it going to make any difference? It's not going to, is it? It's going to get, again, it's going to get dwarfed by that leading term. The leading term is still going to dominate, even though that one oscillates. The oscillations become so tiny compared to that leading term as x gets really big that we just forget about it. So moral of the story then is, how would we treat this limit? As if it were rational, exactly. So what are we going to do? I could set this limit equal to the limit, as long as we're approaching infinities, the black limit equals what simpler blue limit? Six x over 2x. Well, what's that limit equal to? The x's cancel, so what do I get? 3. Boom, there you go. How about that? Okay, make sense? Okay, so that's our, I guess we found our horizontal asymptote, didn't we? Right? So that's telling us horizontal asymptote at y equals 3. Are there any vertical asymptotes? 1? Almost. -1, right? -1 is a 0 of the denominator, but it's not a 0 of the numerator, right? So we'd get a vertical asymptote at x equals -1, okay? And if we look at this guy, let's see here. I think I've got this. Looks like I have the wrong function graphed, unfortunately, though. I have it, not 6x. Well, we'll come back to this. Is that making sense? Okay, I'll put the assignment up. We're not done. We got some more stuff to do, but you could get a jump on it. Have a great weekend.